pH equals negative log H positive, POH equals negative log OH negative, pH plus POH equals 14 at 25 degrees Celsius, pH is less than 7, it's acidic, pH is equal to 7, it's neutral, pH is greater than 7, it's basic. Log BX equals Y turned into BY equals X. For K calculations, for any weak acid reaction simplified as HA double arrow H plus A negative. Ka expression, K equals H plus A minus over HA. Remember that K equals products over reactants. Ice table shortcut, so for weak acids starting with an initial concentration, C, the equilibrium concentration, and roughly becomes H plus equals H, A minus equals X, H plus equals C, so it simplifies to K equals X squared over C, where X equals H positive. pKa relationship, so pKa equals negative log Ka, Ka equals 10 to the power of negative pKa. Rule of thumb, a lower pKa or a higher Ka means a stronger acid. Writing Ka equations, put acid on reactant side with water, so HA plus H2O turns into H3O plus A negative, or just H plus turns into H plus A minus. 2, take away H plus from starting formula for conjugate base A minus, dropping charge by 1. 3, write the expression products over reactants, leaving out liquid water. Finding K and pK from pH. So 1, find H positive. Use H positive equals 10 to the power of negative pH. This value is your X. 2, plug X and initial concentration C into Ka equals X squared over C. Find pKa. pKa equals negative log Ka. Finding H plus and pH from Ka. 1, rearrange K equals X squared over C, solve for X. X now equals square root Ka times C. 2, calculate X. This gives you your H positive. 3, find pH. pH equals negative log H positive. Percent ionization and Kb. Strong versus weak. So substance type, strong acid slash bases. So HCl, HNO3, NaOH, BaOH22. So how it behaves, dissociates 100%, no equilibrium, no ice table. How to solve it, acids H plus equals initial concentration, bases OH negative equals initial concentration, X number of OH ions. So substance type, weak acid slash bases, benzoic acid, hydroxylamine, NO3. How it behaves, dissociates partially, must use equilibrium constants. Use ice shortcut, so weak acids, Ka equals X squared over C, where X equals H positive. Weak bases, Kb equals X squared over C, where X equals OH negative. Kb and percent ionization. Kb expression for a weak base reaction, B plus H2O turns into BH positive plus OH negative. Kb equals BH plus. It's basically reactants over, products over reactants. Conjugate relationship, so Ka times Kb has to equal 1 times 10 to the power of negative 14, or pKa plus pKb equals 14. Rule of thumb, the stronger the acid, the weaker its conjugate base. A higher pKa means a stronger conjugate base. Present ionization formula, so equilibrium H plus or OH negative over initial concentration of acid or base times 100%. You have to use ice table and Ka to solve for this. Strong acids and bases. 1, count the ions. 2, convert grams if needed, so moles equals mass over molar mass. Divide by volume for molarity. 3, finish logs. Weak acid slash base equilibrium. Find your X, H plus equals H or OH negative equals X. 2, solve for the unknown. Plug X and the C into your K or Kb to solve for missing constant. Ka for acetic acid is 1.8 times 10 to the power of -5, by the way. Weak bases with pH. 1. Shift pH to POH. POH equals 14 minus pH. 2. Find OH negative. OH negative equals 10 to the power of negative POH, which equals X. 3. Solve for Kb. Kb equals X squared over C. Acid-base salts, salt hydrolysis. Ion origin, strong base, Na plus, K plus, lithium plus. Strength, spectator, effect on pH, neutral, no effect. Ion origin, strong acid, Cl negative, NO3 negative, Br negative. Strength, spectator, effect on pH, neutral, no effect. Weak base, NH4 plus, CH3, NH3 plus. Strength, conjugate acid, effect on pH, acidic. Ion origin, weak acid, ClO negative, NO2 negative, F negative. Strength, conjugate base, effect on pH, basic. Strategy, the parent rule. For any salt, identify the parent. So positive ion, Na plus, comes from NaOH, a strong base. It is neutral. 2. Negative ion, ClO negative, comes from HClO, a weak acid. It acts as a base. 3. Result, since the base side is stronger than the acid side is weak, the solution is basic. Determining acidic/basic/neutral. Both parents strong, e.g. Cl3 from KOH and HCl. Neither ion reacts with water. Result, neutral. Strong base plus weak acid parent. So example, NaNO2. The weak acid conjugates NO2 negative, makes it basic. Weak base plus strong parent. So example, NH4Br. The weak base's conjugate, NH4 plus, makes it acidic. Comparing Ka and Kb. When both ions come from weak parents, like NH4F, they both try to change the pH. You must compare their strengths. 1. Identify the Ka of the cation and Kb of the anion. 2. Compare values. So if Ka is greater than Kb, the solution is acidic. If Kb is greater than Ka, the solution is basic. K is approximately equal to Kb, the solution is neutral. And for protic salts, for ions like HCO3 negative, they can act as both an acid and a base. Check the Ka of HCO3 negative versus the Kb of HCO3 negative. Since Kb of bicarbonate is generally higher than its Ka, NaHCO3 solutions are basic. If the cation is from group 1 or 2, except beryllium/magnesium, ignore it, it won't change the pH. Focus only on what the anion is doing. Okay, titrations and buffers. The Henderson-Hesselbach equation for buffers. pH equals pKa plus log conjugate base over weak acid. Use this for buffer solutions when you mix a weak acid/base with its conjugate salt. The equivalence point rule. Strong acid plus strong base, pH equals 7. Strong acid plus weak base, pH is less than 7. Acidic due to salt hydrolysis. Weak acid plus strong base, pH is greater than 7. Basic due to salt hydrolysis. Indicator rule. Choose an indicator whose color change range, pKin, matches the pH at the equivalent point of your specific titration. Weak base calculations from pKb. 1. Convert pKb to Kb, so Kb equals 10 to the power of negative pKb. 2. Find OH negative. Use weak base shortcut. X equals Kb, square root Kb times C, where X equals OH negative. 3. Find POH and pH. POH equals negative log OH, then pH equals 14 minus POH. Salt hydrolysis and litmus test. Blue litmus turns red in acidic solutions. Red litmus turns blue in basic solutions. Identify active spectator. Identify active conjugate. The anions are weak conjugates that accept protons from water, releasing OH negative. Indicator selection. 1. Identify the titration type. 2. Match pH. Phenolphthalein changes color in a basic range, pH 8 to 10. Ethyl red or methyl red changes color in an acidic range, pH 4 to 6. Choose which are that match the acidic equivalence point. For buffers, pH calculations, use Henderson-Hesselbach equation if the concentration of the weak acid equals the concentration of the conjugate base, so pH equals pKa. For adding smaller amounts of strong acid, H+, the conjugate base consumes it, so base decrease, acid increases. For adding small amounts of strong base, OH negative, the weak acid consumes it, acid decreases, base increases. The core log scale and trends value with P in front of it, scale is inverted because of the negative log. So high K/Kb, low pKa/pKb, stronger acid or base. Temperature and Kw shifts, autoionization of water, H2O turns into H++ OH negative, is endothermic. Raised temperature equals equilibrium shifts right, which turns into Kw increases, which becomes larger than 1 times 10 to the power negative 14. So H+ increases, so the neutral pH value drops below 7. The water is still neutral because H+ equals OH negative, but the neutral point on the scale has shifted. Titration curves and regions. 1. Initial pH right at start, V equals 0. If it starts low, it's an acid in the flask. If it starts high, it's a base. 2. The buffer region, half equivalence point, flat plateau-like region. Concentration of weak species equals its conjugate pair, meaning pH equals pKa or POH equals pKb. 3. Equivalence point, steepest vertical section of the curve where moles of acid equals moles of base. Look at pH to find unknowns. pH equals 7, strong plus strong. pH is greater than 7, weak acid plus strong base. pH is less than 7, strong acid plus weak base. Buffer mechanics and stoichiometry. So the stoichiometry box before equilibrium, strong acids/bases react 100%. Use a simple mole subtraction / addition table to find what's left over. If adding strong acid, H+, it consumes the base form. Base moles decrease, conjugate acid moles increases. If adding strong base, OH negative, it consumes the acid form. Acid moles decrease, conjugate base moles increase. Step 2, the equilibrium calculation. Take your remaining moles, divide them by the new total volume to get moralities, and plug them into the Henderson-Hasselbalch equation to find the final adjusted pH. Structural deep understanding. To apply equilibrium ideas to unfamiliar chemical structures, look for specific functional groups. Identifying weak acids, look for the carboxylic acid group, so attachment COOH. The hydrogen on the oxygen is acidic because the resulting negative charge can resonate across both oxygen atoms, stabilizing the conjugate base. Identifying weak bases. Look for amines, functional groups containing nitrogen with a lone pair like NH2 or NH. The lone pair on the nitrogen acts as a Bronsted-Lowry base by accepting a proton H positive. Solubility and intermolecular forces, IMFs. Uncharged organic acids/bases are often nonpolar or moderately polar, held by dipole or dispersion forces if the carbon chain is long and have lower solubility in water. Once they ionize into their salt forms, so COO negative or NH3+, they can form incredibly strong ion dipole forces with water, dramatically increasing their solubility. So state matters. Always write out state symbols in your equation. Remember that pure liquids and solids are left out completely for Ka/Kb expressions. And yeah.